Protostars represent the earliest stage in stellar evolution, forming within the dense molecular clouds that permeate our galaxy. They are essentially stellar embryos, masses of gas that have begun gravitational collapse, but have not yet reached the temperature and pressure conditions necessary for nuclear fusion. The protostar phase typically lasts approximately 500,000 years for low-mass stars like our Sun, though this duration can vary significantly depending on the star's ultimate mass. During this critical developmental period, protostars accumulate material through accretion, gradually increasing in temperature and density until they eventually transition to pre-main sequence stars, and finally to main sequence stars, when nuclear fusion begins. This fascinating process of stellar birth, first theoretically proposed by Soviet physicist Viktor Ambartsumian, and later refined by Chushiro Hayashi in 1966, has been extensively studied through infrared and radio astronomy, revealing the complex mechanisms behind star formation. Molecular clouds, often referred to as stellar nurseries, serve as the birthplace of stars throughout the universe. These immense interstellar structures consist primarily of molecular hydrogen, H2, and helium, along with trace amounts of more complex molecules and cosmic dust. The molecular nature of these clouds, as opposed to atomic or ionized gas, is crucial for star formation, as molecules can more effectively radiate away energy, allowing the cloud to cool and contract. Giant molecular clouds can contain as much as 10 million times the mass of our Sun and extend for hundreds of light years across space, harboring the potential for thousands or even millions of future stars. The internal structure of molecular clouds is far from uniform. Rather, these cosmic clouds contain regions of varying density, with some areas being significantly more concentrated than others. This uneven distribution of matter plays a critical role in initiating the collapse process that leads to protostar formation. The densest portions of molecular clouds have sufficient gravitational pull to begin attracting surrounding gas and dust, creating seeds for future stellar systems. These density variations can arise from various factors, including turbulence within the cloud, interactions with neighboring clouds, or the disruptive effects of nearby supernova explosions. Astronomers have identified more than 100 different types of molecules within these clouds, many forming on the surfaces of interstellar dust grains before being released into the surrounding environment. This chemical diversity contributes to the complex dynamics of molecular clouds and influences the properties of the stars that will eventually form within them. The temperature within molecular clouds typically ranges from 10 to 50 Kelvin, 263 to 223 degrees Celsius, cold enough to allow gravity to overcome the thermal pressure that would otherwise prevent collapse. For a molecular cloud to begin forming protostars, certain conditions must be met. The balance between gravitational forces pulling inward and gas pressure pushing outward is critical. When these forces exist in equilibrium, the cloud remains stable. However, various events can disturb this delicate balance, triggering the collapse process. Galaxy collisions, which compress clouds as they interact, represent one such trigger. Similarly, shock waves propagating from supernova explosions can compress regions of a molecular cloud, initiating local collapse. The gene's mass, the minimum mass required for a cloud to collapse under its own gravity, is a fundamental concept in understanding the initiation of protostar formation. When a region of a molecular cloud exceeds this critical mass, gravitational attraction overwhelms the internal pressure, and the collapse process begins. For typical molecular cloud conditions, this mass threshold is on the order of several solar masses, though it varies with temperature and density. As collapse proceeds, the cloud fragments into smaller clumps, each potentially forming an individual protostar or small group of protostars. When the delicate equilibrium within a molecular cloud is disturbed, gravitational collapse begins in regions where the density exceeds a critical threshold. As these regions start to contract, their gravitational influence strengthens, accelerating the collapse process in a self-reinforcing cycle. The initial stages of collapse proceed relatively slowly compared to later phases, as the cloud must first overcome internal pressure and magnetic fields that resist compression. During this early period, the collapsing cloud remains optically thin, allowing radiation to escape efficiently and keeping the temperature relatively stable. The uneven distribution of matter within molecular clouds causes some regions to have greater mass and consequently stronger gravitational fields. These areas become centers of attraction, drawing in surrounding material and initiating the formation of distinct protostars within the larger cloud complex. A single molecular cloud typically fragments into numerous collapsing regions, each evolving somewhat independently while still interacting with neighboring fragments. This fragmentation process explains why stars commonly form in clusters rather than in isolation. As cloud fragments collapse, conservation of angular momentum causes them to spin increasingly faster, similar to how a figure skater spins more rapidly when drawing their arms inward. This rotation plays a crucial role in shaping the evolving protostellar system. The rotational motion prevents all material from falling directly onto the central protostar, instead causing it to form a flattened, disc-like structure surrounding the nascent star. This protoplanetary disk later becomes the site of planet formation, connecting the processes of star and planet birth into a unified evolutionary sequence. The distribution of angular momentum presents a significant challenge known as the angular momentum problem in star formation theory. While observations confirm that molecular clouds contain substantial angular momentum, mature stars rotate much slower than would be expected if they had retained all this initial rotation. Various mechanisms help resolve this discrepancy, including magnetic braking, the formation of binary or multiple star systems, and bipolar outflows that eject material perpendicular to the rotational disk. The protostar phase officially begins when the collapsing cloud fragment forms an opaque, pressure-supported core at its center. This core represents the embryonic star, though it bears little resemblance to the mature star it will eventually become. Initially, the core is relatively cool and large compared to a main sequence star of equivalent mass. As the collapse continues, gravitational potential energy converts to thermal energy, gradually heating the core and surrounding material. This released energy creates a pressure gradient that temporarily slows the collapse, establishing a quasi-equilibrium state for the early protostar. The process by which a protostar gains mass is known as accretion. Material from the surrounding cloud falls toward the protostar, accelerating as it approaches due to the increasing gravitational pull. This infalling matter forms an accretion disk around the protostellar core due to conservation of angular momentum. The disk channels material onto the protostar while redistributing angular momentum outward. The rate of accretion varies throughout the protostellar phase, generally decreasing over time as the surrounding reservoir of material depletes. For solar mass protostars, typical accretion rates range from 10 to 8 to 10 to 5 solar masses per year. As the protostar continues to collect material, the surrounding accretion disk evolves in structure and composition. This disk, often called a protoplanetary disk or proplide, contains the raw materials for future planet formation. Observations with the Hubble Space Telescope have provided direct visual evidence of these disks around young stellar objects in regions like the Orion Nebula. These structures typically extend hundreds of astronomical units from the central protostar and contain a rich mixture of gas and dust. Within the disk, complex physical processes unfold that will eventually lead to planet formation. Dust particles collide and stick together, forming increasingly larger aggregates. Gas in the disk provides drag forces that affect the motion of these solid particles, while temperature gradients create distinct regions suitable for different types of planetary bodies. Closer to the protostar, where temperatures are higher, only refractory materials can condense into solids, while volatile substances remain gaseous. Further out, at greater distances from the central heat source, ices and other volatile compounds can condense, providing additional material for planetary building blocks. As accretion continues, the protostar's internal temperature gradually increases due to gravitational compression and the kinetic energy of infalling material. This heating is most pronounced at the center, creating a temperature gradient from the hot core to the cooler outer layers. Initially, energy transport within the protostar occurs primarily through convection, with large-scale fluid motions carrying heat from the interior to the surface. As the internal temperature rises, radiative transfer becomes increasingly important in certain regions of the protostar's structure. Unlike mature stars, protostars derive their energy primarily from gravitational contraction rather than nuclear fusion. This gravitational energy release causes the protostar to shine, though most of this radiation is absorbed by the surrounding dust envelope and re-emitted at infrared wavelengths. The temperature at the core continues to climb throughout the protostellar phase. When it reaches approximately 10 million degrees Celsius, conditions become suitable for hydrogen fusion, marking the end of the protostar phase and the transition to a pre-main sequence star. Astronomers classify protostars into several evolutionary stages based on their spectral energy distributions, which reflect different phases in the star formation process. Class 0 protostars represent the earliest observable stage, where the central protostar remains deeply embedded within its dusty envelope. These objects emit primarily at far infrared and submillimeter wavelengths and are characterized by powerful bipolar outflows. The protostar mass at this stage is typically less than that of the surrounding envelope. Class 1 protostars have evolved further, with the central object now containing more mass than its surrounding envelope. These protostars emit strongly in the mid-infrared and display less powerful outflows than their Class 0 counterparts. The accretion process continues actively during this phase, though at a declining rate. Class 2 objects, also known as classical T Tauri stars for low-mass protostars, have largely cleared their surrounding envelopes, revealing the central star and its protoplanetary disk. By the Class 3 stage, the disk has thinned considerably, and accretion has largely ceased, marking the transition to the pre-main sequence phase. One of the most dramatic features associated with protostars is the presence of bipolar outflows, powerful streams of material ejected perpendicular to the accretion disk along the protostar's rotational axis. These outflows take the form of collimated jets that can extend several light years from the central protostar. The exact mechanism driving these jets remains an area of active research, though it likely involves the interaction between the protostar's rotation, magnetic fields, and the accretion process. Bipolar outflows serve several important functions in protostellar evolution. They carry away excess angular momentum, helping to solve the angular momentum problem. They also clear paths through the surrounding envelope, eventually creating channels through which radiation can escape more easily. Additionally, as these high-velocity jets impact the surrounding medium, they create shock waves that compress gas and potentially trigger further star formation in adjacent regions of the molecular cloud. The energy and momentum injected into the cloud by multiple protostellar outflows may also help support the cloud against global gravitational collapse. The evolutionary path and characteristics of protostars vary significantly depending on their mass. Low-mass protostars, those that will become stars less than about 2 solar masses, evolve relatively slowly, with the protostellar phase lasting hundreds of thousands of years. These objects undergo a gradual transition from the protostellar to the pre-main sequence phase, often passing through a T Tauri phase, characterized by strong stellar winds that help clear away remaining circumstellar material. In contrast, high-mass protostars, those destined to become O and B-type stars, evolve much more rapidly, sometimes reaching the main sequence while still actively accreting material. Their intense radiation can ionize the surrounding hydrogen, creating H2 regions that help disperse the protostellar envelope. This rapid evolution presents challenges for observation, as high-mass protostars may spend their entire pre-main sequence lives deeply embedded within their natal clouds. The formation mechanism for these massive stars remains less understood than for their lower-mass counterparts, particularly regarding how they overcome radiation pressure that might otherwise halt the accretion process. For low-mass protostars, the T Tauri phase represents an important transitional stage between the protostellar and main sequence phases. Named after the prototype star T Tauri, these objects exhibit strong stellar winds and significant variability in brightness. The powerful winds, much stronger than the solar wind, help disperse the remaining envelope of gas and dust surrounding the young star. T Tauri stars are divided into 2 categories: classical T Tauri stars, which still possess substantial circumstellar disks and show evidence of ongoing accretion, and weak-lined T Tauri stars, sometimes called naked T Tauri stars, which have largely cleared their surrounding material. The T-Tauri phase typically lasts several million years, during which the star continues to contract and increase in temperature. During this time, the protoplanetary disk evolves significantly, with planet formation processes well underway. Observations of T-Tauri stars provide valuable information about the late stages of star formation and the early evolution of planetary systems, offering insights into the processes that shaped our own solar system billions of years ago. Studying protostars presents significant observational challenges due to their embedded nature. Visible light cannot penetrate the dense dust envelopes surrounding young protostars, necessitating the use of longer wavelength observations. Infrared astronomy has proven particularly valuable for protostar studies, as infrared radiation can pass through dust more effectively than visible light. As protostars heat their surrounding dust envelopes, this dust re-radiates energy at infrared wavelengths, creating distinct spectral signatures that astronomers can detect and analyze. Radio astronomy complements infrared observations by probing different aspects of protostellar systems. Radio waves can penetrate the dense dust completely, revealing the innermost regions of protostellar envelopes and accretion disks. Molecular emission lines observed at radio and submillimeter wavelengths provide information about the chemical composition, temperature, and velocity structure of the gas surrounding protostars. These observations have identified complex organic molecules in protostellar environments, suggesting that the chemical precursors to life may form during the earliest stages of stellar and planetary evolution. The Orion Nebula stands as one of the most studied star-forming regions, offering astronomers a relatively nearby laboratory for investigating protostellar evolution. Located approximately 1,500 light-years from Earth, this nebula contains hundreds of protostars at various evolutionary stages. Hubble Space Telescope observations of the Orion Nebula have revealed numerous protoplanetary disks, providing direct visual evidence of the structures where planets form. These observations support theoretical models of star and planet formation, while revealing unexpected features that continue to refine our understanding. Another significant observational target is the Eagle Nebula, M16, made famous by the Hubble's Pillars of Creation image. This region contains numerous evaporative gaseous globules, EGGs, which are essentially the same structures as protoplanetary disks, but viewed from a different angle. These EGGs are illuminated and partially shaped by ultraviolet radiation from nearby massive young stars, illustrating how star formation in one region can influence protostellar evolution in adjacent areas. Similar structures have been observed in other star-forming regions, suggesting this is a common aspect of clustered star formation. The protostar phase concludes when the central object reaches a temperature sufficient to initiate nuclear fusion of hydrogen into helium, approximately 10 million degrees Celsius at its core. This transition marks the birth of a true star, though not yet a main sequence star. The initiation of fusion dramatically changes the energy balance within the star, as nuclear reactions begin to contribute significantly to the energy output previously dominated by gravitational contraction. For solar mass stars, this transition typically occurs after about 500,000 years of protostellar evolution. The specific nuclear reaction that first activates depends on the mass of the protostar. For stars less than about 1.3 solar masses, the proton-proton chain dominates, while more massive stars primarily use the CNO, carbon-nitrogen-oxygen cycle. Both processes convert hydrogen to helium, releasing energy in the form of gamma rays that gradually work their way to the surface, where they emerge primarily as visible light. This nuclear ignition stabilizes the star against further gravitational collapse, establishing a new equilibrium state. After nuclear fusion begins, the star enters the pre-main sequence phase, continuing to contract and evolve toward the main sequence. During this period, the star's internal structure reorganizes as energy transport mechanisms shift from being primarily convective to incorporating significant radiative zones for stars above about 0.3 solar masses. The star's luminosity and radius decrease during this contraction, while its surface temperature generally increases. These changes cause the star to follow a distinctive track on the Hertzsprung-Russell diagram, known as the Hayashi track for fully convective stars and the Henye track for stars developing radiative cores. The duration of the pre-main sequence phase varies dramatically with stellar mass. Massive stars may reach the main sequence in just thousands of years after leaving the protostar phase, while the lowest mass stars can take hundreds of millions of years to complete this transition. Once a star's core reaches the temperature and density where hydrogen fusion can precisely balance the gravitational force, it joins the main sequence, the stable, hydrogen-burning phase where stars spend the majority of their lives. Our Sun, for instance, will remain on the main sequence for approximately 10 billion years total, with about 5 billion years already elapsed. The formation of protostars represents one of the most fundamental processes in astrophysics, connecting the diffuse matter of interstellar space to the concentrated energy sources that sustain planetary systems. Beginning with the gravitational collapse of molecular cloud fragments, protostars evolve through a series of stages characterized by accretion, heating, and eventual nuclear ignition. Throughout this process, the conservation of angular momentum shapes the formation of protoplanetary disks, setting the stage for the potential emergence of planetary systems similar to our own. The study of protostars continues to advance with increasingly sophisticated observational capabilities. Infrared and radio telescopes provide windows into the dust-enshrouded environments where stars are born, while theoretical models and computer simulations help interpret these observations within a comprehensive framework of stellar evolution. Each new discovery refines our understanding of how stars form, illuminating the processes that gave rise to our own Sun and, by extension, to life on Earth. As we continue to observe and analyze protostars across our galaxy, we gain deeper insight into the cosmic cycles of matter and energy that have shaped our universe throughout its history.